So in problem number 60, we have a playground merry-go-round with radius 2 meters that has a moment of inertia of 275 kilogram meters squared, and it's rotating around a frictionless vertical axis. As a child of mass 25 kilograms stands at a distance of 1 meter from the axle, the system rotates at 14 revolutions per minute. The child then proceeds to walk towards the edge of the merry-go-round. What's the angular speed of the system when the child reaches the edge? So this is one of those classic before and after ones or pictures with angular momentum. The picture to the left shows beforehand, picture to the right afterwards. So what do we have in this case? We have to consider the angular momentum, which is going to be I times omega. The problem is we have to figure out what I is. We've got the disk, but we also have to include the student who's sitting on it. So the general definition of rotational inertia is the sum of each mass times r squared. But in this particular case, we've got the disk. They actually already gave it to us, the merry-go-round, which is the disk. And then we've got to consider the student standing 1 meter away from the center. So solving this one, we take the disk, which is 275, and then add to it the child, which is just their mass times how far they're away squared. If you add that together, we get 300 kilogram meters squared. We also need to figure out omega. They gave it to us in revolutions per minute, not friendly units. Eventually, I assume we want the angular speed in radians per second for this one. So converting here, 14 revolutions per minute, 2 pi radians in each revolution, and then, of course, 1 minute is equal to 60 seconds. And if you divide that out, you get 1.47 radians per second is the initial angular velocity of the system. Plugging in our numbers now, we know the rotational inertia is 300 from down below. We know omega is this from right here. And if you multiply it out, we get that the total angular momentum before the system, before the child moves, is 440 kilogram meters squared per second. That has to be true as well when the child moves towards the outside edge. So angular momentum must be conserved. Before we solve it, though, real quick, what's the new rotational inertia? It changes. The disk or the merry-go-round doesn't change, but the position of the child does. The child is now 2 meters from the center at the edge of this thing. And so 2 squared is 4, plus times 25 is 100, plus 275, gives us a new rotational inertia of 375. We know the angular momentum has to be conserved. It was 440 here. It's got to be 440 here. Again, that's what L stands for. I is now changed to 375 from down below. And if you solve for omega, this thing will now slow down. It was going 1.47 radians per second. It's now going to rotate at 1.17 radians per second. Why? Because the rotational inertia has increased.